Hello, so the purpose of this video is to go into a little more detail on actually constructing the bounding volume hierarchy. But before I get into that, I just want to run through something super quickly. One of the comments in my video, Arnon, thank you Arnon, was pointing out that perhaps my BVH traversal was not optimal, and I found out that yeah, it wasn't. So just to start with, I'll fire this off, we'll see how we go. There we go. So this is 1024 spheres, 4 rebounds, 4 sample anti-aliasing, and yeah, to an optimal frame rate of 60 frames per second, give or take 10. So the resolution indicates the performance, we could say. So we can see the performance here. It is what it is, not the worst. Could be worse, I'd say. But let me just modify the shader code here. So we'll go to this shader, and it's in this trace function. So the way this is working is we track the next node that we want to visit, and we go along in a non-decreasing manner. So we basically spin an empty cycle of the for loop if we don't hit the next node. But I mean, why? If that makes sense. So why not simply unpack the node, and then we'll do a while loop, and we'll go while that next node index is bigger than or equal to 0, because the terminal test, the terminal condition is -1. So if next node index gets set to -1, that will break out of this loop. Otherwise, it will continue as normal. Now let's give that another shot. And now this is the resolution that we can have. As you can see, it is improved. And an improvement is always welcome, especially when it's just an error on my part. So it's very cool. As it turns out, I experimented with this a little bit, and we can improve it a little bit more, because now this traversal is properly exiting the loop. And that means that it's okay to increase the number of internal nodes. So we can go to the scene, and in the subdivide section, we have a maximum of 16 spheres per box. We can reduce that quite a bit and see how that improves our performance. So there we have it. Perhaps not the highest performance, the biggest increase, but as you can see, we're sort of resolution breathing. So we're sitting on the threshold between 2 resolution levels, which I find interesting. But anyway, there we have it. So that's just a little improvement, and the code which is in the GitHub repo as of uploading this video will include the improved traversal. I just like to walk around. I think this is pretty cool. Anyway, so enough of that, and on with the example. Okay, so here we have a scene. The scene has 8 spheres, and they are arranged. Now the goal is to subdivide this into smaller areas hierarchically. So what I'll do first of all is each box will have a bunch of spheres, and what I'll be doing is dividing that space up and then throwing the spheres into different boxes. Now, what I could do is hold a pointer to the spheres or something, but it's probably a better idea if I want to throw references to the spheres into other boxes, but I don't want to mess up the original ordering of the spheres in my scene, in my database, then one approach is to take an array. So this will be the indices of all the spheres. We start off with pretty much the natural order, and portions of these will be referred to by the regions of the bounding volume hierarchy. So the first thing I'll do is I'll say, okay, we have node 0, and let's throw all the spheres into that node. So all of these spheres, this region, will belong to the root node 0. Then we progressively look through and find the extent. So if we just looked at this sphere here, it would be very small. Then we include this sphere number 1, and we basically find the maximum and minimum x and y for this example to tightly bound all of these spheres. So these are all the spheres in the root. Then we look in the two axes and we find, okay, in the length and the width, which of those is the largest? So in this case, it's the x, it's the length. Then we halve that length. And this x value, halfway along, is our pivot. So then we look through and we say, okay, well, the start position is 0, the end position is 7. Thing at the start, thing number 0, is that in the left or right? It's in the right, so I want to actually swap it to put it on the right-hand side. So as per the in-place quicksort algorithm, we swap these two, and then we bring our forward position, our end position, forward by 1. So now we're looking at 6. Now we look at thing number 7, position 0, thing number 7. Is that in the left or right? Well, it's also in the right, so we'll need to swap that around. The thing here is position number 6, so we'll swap that in. Thing number 7, bring our end index forward by 1. Now thing number 6, oh yeah, there it is, okay, is in the left, so that's fine. We can look at the next position. Thing number 1 is in the right, so we'll swap it with thing 5. And then we say, okay, thing number 5, oh yeah, bring our end position forward by 1. Turns out it's also on the right, so we'll swap it with our end position, which is thing number 4. 4, 5. I'll bring this forwards. Okay. I'm going crazy. Okay. So then we say, okay, the next thing here is, number 4 still. Number 4 is on the left. Okay, so that's fine. Bring the start position forward by 1. Then we have position, sphere number 2 is in the left. Okay, that's fine. Bring that forwards. Okay, now we're on thing number 3. By the way, thing number 3, well, we're done. It's on the right. So I know that's a lot of fun to watch in real time, but that is literally how the algorithm works. By the way, I messed up a little bit on previous video here. I said that the time was n log n. This operation itself is just log n. Yeah, it's just log n. And then if we keep splitting our space in half, then you'll have log n splits. And so the total, in the best case, the total for quicksort is n log n. But anyway, so then I look here and I track this with variables and I say, well, we had 3 things in our left half. And then we look here, that's our right half. Now we're going to go depth first search, so we'll split on the left first. This was node number 0, so now this thing will call that node number 1, is this region of spheres, as we can see here. So we'll put that there, that's the left child. And then, again, we'll grab all the spheres in here and use those to work out our extent. So the extent for node number 1 is that region there. Okay, and then we'll have a look at that. Actually, Anyway. Okay. So then we'll look at this extent and we'll say, okay, which of these is a larger axis? Well, the width here is larger, so we'll split halfway across the width, and then we'll have these two regions here. So we compare, okay, thing number 6, is that in the upper? Yes, it is. Okay, thing number 4, is that in the upper? No, it's not. So we'll have to swap those around. And you can see how this is going. So thing number 2 is in the upper. Yes, thing number 4 is in the lower. So this gives us our partition on that region. Now, this partition, we had node number 1, so we'll go node number 2. We try to subdivide node number 2. We can't, because I'm going to bring it down to two spheres maximum. And then node number 3, we'll say, is this bottom one. But we will potentially shrink these regions a little bit just to keep them tight. Okay, so again, the regions shrink, but they don't subdivide because the number of spheres in those regions is less than or equal to 2. So we're content. We can load these as external nodes. Okay, then we look at this other part. So this other part now, we have done 1, 2, 3. This other part will be node 4. So we have a look at node 4. We shrink the bounds. That's probably fine. Okay. And then we compare which is larger, the X or the Y. It's pretty even. I'd say maybe the Y. So let's split that one. And then we will partition everything. These little notes down the bottom are just for handy reference. So let me look here. We go through the same algorithm. Number 3 is on the bottom, so we'll swap that around. Thing number 0 is in the top, yes. Thing number 5 is in the top, good, we can keep that. Thing number 1, sphere number 1 is in the bottom, so we'll swap that around. And then 7 is in the top. Yep, okay, good. So that is our partition there. Again, we'll work on, this will be node number, what we have 4, so this will be node number 5. Split that up. And then I'll go through this a little more quickly. Okay, so we can see, give or take, the X is a larger dimension, so split that way. And then that'll give us node number 6 here is external. Node number 7 here is external. And then if we work on the bottom node here, split this up, grab the extent there, this will be node number 8, and that will be external. So that is the way this algorithm is working. Now, the next thing we need to do is we need to work out the hit and miss links. So I'll just note here, we just like before, I have a terminal sentinel value there of -1. The hit or miss link is an integer indexing into the node that we want to look at. So for instance, let's do our hit links. Okay, so let's say we start at the VirtualBox node 0 and we hit it. Okay, well then the next thing we want to investigate is its left child. Okay, then we're at number 1. Let's say we hit number 1. Is node number 1 internal? Yes, it is. So the hit link is its left child. Then we go to node number 2. Is node number 2 internal? No, it's external. So it will be the parent's right child. So we query node number 1. What's your right child? It says it's this one here, node 3. Then we look at node 3. If we hit node 3, it's external. So we want to be the parent's right child. So we go, okay, node 1, what's your right child? It says it's you. Okay, ask its parent, what's your right child? So that's node number 4. So the point is, if we hit something, we want to keep testing to see if we hit other things, because it could turn out that the things in node 4 are actually closer than that sphere that we hit in node 3. Okay, so again, node 4, hit link, it's the left child because it's internal. Node 5 is internal, so its hit link is the left child. Node 6 is external, so it's the parent's right child. Node 7 is external, so it's the parent's right child recursively. Now, node 8, its parent essentially is the root. And so if we hit node 8, we have nothing else to test. We are done. Now, this might seem like a bit of a nightmare if we hit every single thing. Yeah, it basically is. But we also have mislinks. So we look at the root node, that's this whole scene. If we miss that whole scene, we are done. Okay, then we go to node 1. So if we hit the root, we test node 1. If node 1 fails, what should we test? We should test the parent's right child. Node 2, well, if we miss node 2, we'll check because it's external, we check the parent's right child. Okay, node 3, again, we'll test the parent's right. Okay, so take 3. My phone is being really weird at the moment. It says it's not recording video, but it is recording files. I don't know. Really weird, but the point was I went through the example of going by hand and linking all of these, linking the tree up basically. What this is doing is pre-baking the traversal order, and it's not bad. It does accelerate the scene. There is one downside, and that is obviously some traversal orders are better than others. So a technique that I'll look at in a future video is computing a bunch of different orderings where after we set this tree up, we swap the children around based on which direction we want to traverse them in, and then basically saving 6 different copies of the tree, and then querying the appropriate tree based on, in the shader, based on the direction that the ray is going. But I'll look at that in a future video. Yeah, for now I just wanted to overview the process, and yeah, look, I hope that helps. Hope this helps to explain the process, and have a good one. Bye.